Okay, welcome everyone to our 11:30 press conference. This is news from Gale Crater, recent findings from NASA's Curiosity Mars rover. Our participants today are Joy Crisp, Thomas Bristow, Patrick Gazda, and John Grotzinger.
So I'm going to provide a high-level overview of the rover mission, talk about the drilling, why we've been drilling on Mars, and the mineralogy of the mudstones we've been examining so far to set the stage for the next three speakers. So in this slide, I'm highlighting that we've put 15 kilometers on the odometer for Curiosity's rover mission so far. This map shows the rover's path. You can see we started up in the upper part of that yellow path, and the current rover's location, and an approximate route the rover will take going up Mount Sharp to investigate changes in the rock as we drive through younger deposits. This landing site in Gale Crater was chosen because of the extraordinary exposure of rock record that appeared accessible to our rover, and because of the different mineral signatures seen from orbit in the different layers. And this landing site has definitely exceeded our expectations. These dark bagnol dunes running diagonally across the map are basaltic sands that the rover can't drive across. So rather than going straight from the landing site over to Mount Sharp, the rover had to drive a long way to the southwest to get to where there's an opening, a gap in those dunes to go up Mount Sharp. Now in our second extended mission, we're well into the layers that were the prime reason for selecting Gale Crater as our landing site. The mountain is not as steep as shown here, thank goodness. This is a diagram with 14 times vertical exaggeration. As we go along, we expect to learn new things about how environmental conditions changed as a function of time when these rocks were deposited and altered. So far, Curiosity has drilled and analyzed 15 rocks. Earlier in the mission, we chose targets based on each site's specific characteristics, but now that we're faced with a nearly continuous exposure of layered rocks, a systematic spacing will provide a more complete picture. So Curiosity's 4 latest drill holes were taken 25 meters apart in vertical elevation. That's Udam through Sabina. So we have spent, and will continue to spend, a lot of time in the Murray Formation. We didn't know what this was going to be before landing because dust obscures much of the mineral signature. But the rover's view from the surface has shown the Murray Formation to be primarily a lakebed mudstone with variable characteristics. So although the rover doesn't want to be a stick in the mud, it sort of is, and we're finding that mudstones can be interesting. So later in the mission, we'll get to units that had stronger signals from orbit, and these we call the hematite unit, clay unit, and sulfate unit. So again, you might think mudstones would be boring, but they're definitely not. This slide shows the amazing diversity of mudstone mineralogy that we've seen so far. This information comes from the ChemIn instrument, which can fire an X-ray beam through a vibrating cell that contains rock powder that we've delivered from the drill. One thing that stands out is the mineral jarosite, shown in purple, which is an indicator of acidic water. And we saw much more of this jarosite further down in the Pahrump Hills, and now it's at much lower levels, indicating a move away from acidic conditions. And at the same time, the clay minerals shown here in green have gone away and then come back again as we went up the hill. So next, Tom Bristow will be talking about the mineralogic variations we've seen and what they mean. And then Patrick Gazda will talk about chemical trends and how they've been changing. And finally, John will talk about the bigger picture and what it means for sedimentary evolution and habitability. So next we have Tom.
Okay, thank you very much, Joy. So as Joy mentioned, I'm going to go into a bit more detail about the mineralogy that we've looked at with the Chemin instrument as the rover's gone about its traverse and started to ascend Mount Sharp. So I'm going to talk in more detail about 4 particular groups of minerals and how those changes in those minerals are reflecting the evolution of ancient conditions at the Martian surface at Gale Crater. So this is important because it may give us a glimpse of how global conditions on Mars changed through time during the interval that the sediments were deposited. And it's also important because the mineralogy helps constrain the local geochemical conditions. And it gives us a sense for the chemical reactions that could have been utilized by any life that was around to make a living. So by surveying the diversity of minerals as we climb up Mount Sharp, we're essentially surveying the diversity of opportunities for making a living within the lakes and rivers at Gale Crater. So I wanted to draw your attention to the pie charts in this slide. We can call them mud pies if you like, because they're all from mudstones. And so I'm going to talk about 4 different colors on those mud pies. The first one is the light gray slices. These correspond to iron and magnesium rich mafic minerals. And as you can see, the light gray slices are decreasing in size as we've been going up the mountain. So these mafic minerals derive from basaltic volcanic rocks. So these are the main sources of sediment feeding the rivers and lakes at the bottom of Gale Crater. And they're highly susceptible to alteration at surface temperatures involving reactions with water. So we think over time, this trend in mafic mineralogy is showing an increase in aqueous alteration of these mafic minerals. So the second suite of minerals that I want to mention are iron oxides. And we see a complete change in the dominant species of iron oxide minerals as we begin up the mountain. You'll see in the lower pie charts we have black slices, which represent the mineral magnetite. And as we go up the mountain, they're being replaced by red slices, which is hematite. So we're going from a change of an iron oxide that contains partially reduced iron to hematite, which is completely oxidized. The yellow slice corresponds to calcium sulfate minerals. These are chemical precipitates. You can see that they dominate in the most recent samples that we've drilled. We think they're an indicator that waters are getting more chemically concentrated. So those minerals typically form from solutions in a basin that get concentrated and evaporate and cause precipitation of those minerals. Joy mentioned the resurgence in observations of clay minerals. You can see the clays are the green slices of the pies. Close to the beginning of the mission at Yellowknife Bay, we all got really excited about the discovery of clay minerals. And they've kind of waned. We haven't seen them so much around the Marias Pass area and Pahrump Hills, but we're really starting to see a resurgence of clay minerals in the Murray Buttes region that we're sampling right now. So just by looking at this diagram, all the clays are kind of colored in a green color. But what we've learned through the XRD analysis using Chemin is that these clays are not the same. So not all clays are created equal, and we're seeing significant differences in the types of clay minerals that we observed at Yellowknife Bay and up at Murray Buttes. So this was a slide I was told that only a scientist could possibly like this slide, but I like it so much that I wanted to show it to you and try and explain why. So this kind of gives you some insights in how, with the Chemin instrument, with X-ray diffraction, this technique, we can actually measure nanometer scale changes in the size of building blocks that make up the clay minerals in our samples. So you see that panel in the top left-hand side of the diagram with an area highlighted in blue. So those are X-ray diffraction peaks coming from clay minerals, and you can see that we have a slight change in the peak position of clay minerals from the Yellowknife Bay samples as we go to Murray Buttes. So this corresponds to changes in the crystal lattice, so just the crystal structure of our clay minerals. So you can see they're very small, but they have big implications because they imply that there are different metals and metals in different redox state being stuffed into the clay minerals in these two different areas. So those have environmental implications. Down at Yellowknife Bay, you can see the unit cell. This crystal cell was a bit larger, and the dominant chemical species stuffed into the crystal structure here are magnesium and reduced iron. Up at Murray Buttes, we have different unit cell dimensions, and these imply that we have oxidized iron and aluminium in the clay crystals in this region. So this next slide really summarizes the changes of mineralogy as we've gone from Yellowknife Bay up into the Murray Buttes region that I've talked about. So the decrease in crystalline mafics, the increase in calcium sulfates. Now, interpreting mineralogy can sometimes be challenging because minerals can form in different places. They can form in place where the sediment is being deposited, or they can be transported and washed in from elsewhere. But this is really this kind of puzzle is really what makes my job fun, and other members on the Chemin team interpreting this data. That makes our job worthwhile and fun. And we're coming up with a coherent picture that as we're ascending the mountain, we're seeing evidence of increased aqueous alteration of the basaltic minerals that are washed down into the lake under progressively more oxidizing conditions. So I think later on John is going to talk about this and how this fits into the big picture of what's going on at Gale. Before that, Patrick's going to talk about detections of boron and their implications.
Thanks, Tom. So I'll be talking about the boron that we've been measuring with the ChemCam instrument in Gale Crater in these calcium sulfate-filled fractures. The ChemCam instrument, just to remind you, is the laser. Where we take the laser, we can get chemical composition of a small point on a rock from around 7 yards away. And so I'll be talking about why we think the boron is there and why it's important for understanding the geochemistry of Gale Crater. So this is the full traverse map again. And so we've been seeing these calcium sulfate-filled fractures in the Murray Formation and way back at Yellowknife Bay. Sorry. Yellowknife Bay is there. But since driving into this Bagnall Dunes and Murray Buttes region, which is in my inset, we've been seeing boron in these calcium sulfate veins, and this is the first detection of boron on Mars by any mission. The colored dots here on the map are showing where we've detected boron and how much is there based on that color bar that I have on the right. And so you can see that we've had this sharp increase in the number of boron detections in these last few months as we started our drilling campaign and to drive up Mount Sharp. So here's an example of a calcium sulfate filled vein, which is this light tone material surrounded by the Murray bedrock, which is that reddish brown rock. And this is a mass cam image. We targeted this vein called Catabola, which is circled in red there. And in the inset is showing the remote micro image from ChemCam. With the red crosshairs is where we hit each point on the vein. And so the orange bars are giving us this relative amount of boron that I've seen in these veins, with the highest one is being a little bit less than 0.1 weight percent. So boron is this very water-soluble element that we find in places like Death Valley after the evaporation of a lot of water, or it can be found as part of clays in the sediments that form in lake or oceans, like in Gale Crater. So the presence of boron can tell us either about the chemistry of the lake water, or it can tell us about the later groundwater that produced these calcium sulfate veins. In this other example, so we've been seeing this increase also of chlorine detections along with sodium with the boron. So in this particular example, we have this Dioga target with the mass cam on the left and the remote microimage on the right. And so we've detected enrichments of boron, of course, in this vein. Along with, in that 0.3, we have a detection of chlorine, and that corresponds with a high detection of sodium as well. So we have two ideas about how boron could have gotten into these fractures and deposited with the calcium sulfate. So in this cartoon, I'm going to step through the different steps of how to get boron into the fractures. With panel 4 on each one are the same. This is what we would observe on the surface of Mars. So in hypothesis A, which is the top row of panels, if we have boron in the lake, it's dissolved in the lake water, it can get caught up with the clays, as I said before, and so you have boron in the mudstone bedrock. And then later you have fracturing of that bedrock, and groundwater has to come in, and under certain conditions that boron can be extracted from the rock and gets into the water and then gets deposited with the calcium sulfate in the veins. In the second hypothesis, if, say, the lake water had a different chemistry, so you have boron in there, but the boron's not getting trapped into the rocks. Later, when the lake dries out, you have boron salt forming. And you would also have other types of salts, probably, like sodium chloride and the calcium sulfate. So later, when you have groundwater, it moves through. It can dissolve some or all of these salts and then bring the boron down into the fractures to be deposited with the calcium sulfate. So in both of these hypotheses, you'll note that we need to have this late-stage groundwater system that comes in and redeposits the boron. And the difference really between these two hypotheses is the chemistry of the lake water and the groundwater. And so, and the chemistry of the water has an effect on how boron moves around in the system. And so John Grotzinger will now talk about the implications of these groundwater systems.
Okay, so I'd like to summarize a little bit what my colleagues have told you about, and begin again with this mineralogy. Before we landed, we looked from orbit at this Murray Formation and saw a little bit of this and a little bit of that, but weren't really sure of how exciting it would be. And so our plan was always to keep driving uphill to the so-called clay layer, the so-called sulfate layer, the so-called hematite layer. And it turns out that this Murray Formation is really sort of a bonanza of all the things that we intended to study when we picked the landing site. We just got a lot earlier than we thought, but even more exciting is that it's changing across geologic history. And so if you start down at Yellowknife Bay, you're 200 meters lower in elevation than you are up here. So the first point to make is that 200 meters of rock on Earth would be equal to tens of millions to hundreds of millions of years of time. So on Mars, we expect that this is a good conservative estimate because we don't have plate tectonics. We don't have the kind of basins where the floor drops out and would accelerate the sediment accumulation rate. And so all things being equal, it should be roughly that same age. And so when you look at this diagram, what you're seeing is the the consequences of geologic processes operating over those kinds of timescales. And what's important is that early on, we had clay associated with magnetite, as Tom was saying, and that suggests a somewhat more reducing environment. You'll see that there's very little yellow there. Yellow is sort of a proxy for salt. So we once told you guys that this would have been pretty benign water. You could have a glass of it to drink. It wasn't that salty. That's a good thing for habitability. The presence of the magnetite tells you that you have a flow of electrons, that if there had been microorganisms, they would have been available to help drive chemolithotrophic sorts of metabolisms. These are microorganisms that don't need sunlight. They just feed off of the materials that are in the rocks. Then we get to this location, and we see an interesting change. Now we see hematite pick up, so that tells us that there's a redox variability, and again, electrons are flowing around. Now we pick up a little bit more salt, but we also pick up this salt called jarosite, which is a good indicator for more acidic pH. And then you see the next one up, the jarosite increases in abundance. And then after that one, you get to this one, and it decreases in abundance. So it's acid, but it's never really super acid. It's, lower pHs, but totally the kind of environment where an acidophilic kind of microorganism could live and enjoy it. And then we get to this one, and the blue is coming in as the purple is going away, and now we get into this high silica environment. And by the time we get to this one, we've got loads of silica and a very finely laminated kind of rock that would actually be the kind of rock you'd want to get a sample of and bring back to Earth to look for fossil microbes actually preserved in there. Because on Earth, laminated silica is the best type of material we have for recording evidence of life in ancient rocks. And then as we go up, we can see the story changing again, and now we have more clay than we ever saw before coming in, but now it's associated with hematite, as Tom said, and it's also associated with this calcium sulfate. So the waters are getting saltier, but they're nowhere near the salt levels that we had at Meridiani Planum for the Opportunity rover. So it's not so salty that it can't be habitable. It might be seawater salt. If you take a glass of seawater and you evaporate it, that's about how much calcium sulfate would come out of the seawater. And so we see all of the properties in place that we really like to associate with habitability. There's actually nothing really extreme here for the most part. So this is all very good for habitability over very long periods of time. So here's a cartoon that allows you to think about what this means for the bigger picture, because mostly you've heard from us about lakes, but now what we're discovering is that some of the things, the processes we're seeing, like Patrick was talking about with these veins that come in later, we're talking about fractured bedrock that the Opportunity rover is driving across today. The bedrock is mudstone that was once formed in an ancient lake, but it's been broken up much later on and allowed for groundwater to circulate through. So we're confident that not only do the layers of rocks themselves represent very long periods of geological time, but even if the lake dried up and went away, the groundwater would still be circulating. And so we see the deposits from ancient rivers that tell us that there were once liquid water or ice up here that was melting and flowing down to help fill up the lake. So these arrows indicate groundwater that would percolate from accumulation of precipitation, just ordinary rainfall or snowpack up here melting. Same thing from the Gale Central Peak. But then this big arrow coming in from the right, that means that Gale Crater is situated on the Mars dichotomy boundary, where there's a slope going all the way up into the southern highlands. Gale Crater is the lowest point for 1,000 kilometers in any direction. So we could have groundwaters flowing from an enormous range of areas that keep this place wet for a long, long period of time. And so we believe that water was circulating around, interacting with the minerals. If there were microbes of the type that like to live off these basaltic materials, they would have been just as happy down in all these cracks as they would have been up here in the lake, maybe out of the way of other harmful radiation, although we think that in order to have a lake, there would have been a much denser atmosphere, so we've never been too worried about radiation at the time. We think this would have been habitable. So I'll just leave it at that.
Okay, so now we'll open it up to questions. Are there any questions from reporters in the room?
Hi, Irene Klotz with Seeker. For Patrick, I think there was a report like in 2013 about boron in a Mars meteorite. You familiar with that?
Yes.
So could you maybe discuss a little bit about how the findings from Curiosity compare to that, and also for those of us who didn't pay attention in chemistry class, the significance of boron in the ribose and RNA? Thanks.
Oh, so two-part question. Okay, so to address the question about that paper that was written by James Stevenson in 2013. So they measured boron in a Martian meteorite, in one particular Martian meteorite called a Knocklite meteorite. And they found boron in the clay alteration phase. And so, not to diminish the importance of that paper, which was really important, which it also motivated me to be looking for boron on Mars. So the only problem with the meteorite is you don't have the context of all of Gale Crater, or that's the benefit of having the measurement in Gale Crater is that we know a lot about the crater, and there was a lake, and so we have this context that we can bring to the table and leverage that to understand what the boron is doing in the groundwater, for example. And then the second question is about the connection between, I guess what you're going for is this connection between boron and the possible origin of life, okay? So it is thought by some people, Steve Benner is one, that you would need boron in a certain form called a borate, and these borates will react with chemicals, and these chemicals can eventually become RNA. So it's for this RNA world sort of scenario. The only problem with that for this is that we don't know what form the boron is in, because ChemCam can only measure elements. We can't measure the mineral form that the boron is in. So I hope that answers your question.
As Curiosity continues to climb, if the boron concentrations increase, might that measurement be possible, or will you always be restricted just to elements, not minerals?
So the other instrument that could measure, well, it's really the Chemin instrument. So the Chemin instrument can do mineralogy. So if we do find this hypothetical salt layer that I talked about, it's possible that we could get a sample of that and see what is there, if there's enough boron. And then the SuperCam instrument on Mars 2020 will be able to do both element boron, and we'll also have another type of instrument called a Raman spectrometer. We'll be able to measure the type of boron that's there.
Okay, any other questions from reporters in the room? Do we have any questions on the chat?
We do. Emily Lochtawoloff of the Planetary Society asks, you showed a sequence of changing rock types and discussed how they changed as the rover went up. Do you think this is representative of the stratigraphy, or are some of the places you sampled things that were picked because they were atypical and therefore interesting? How representative are the sample locations of the mountain's vertical stratigraphy?
Yeah, that's a good question. Early on, when we were trying to drive to get farther up the mountain, we did stop and drill things that we thought were interesting. But once we got to the Pahrump Hills area, which was the first time we encountered the Murray, we just simply studied it because it was time to begin investigating the Murray Formation. So we took what we got, which was the very first part of it. And then we had to drive over a different kind of rock called the Stimson in order to keep the vehicle safe. But when we got back into the Murray again, we have been sampling, as Joy said, at a systematic 25-meter interval in elevation. And so, if you will, that gives us a more random sampling of what's there without bias towards a particular hypothesis or something that catches our eye.
Okay, do we have any more questions from reporters in the room?
Thanks. John, can you talk a little bit more about the Silica Rocks and if it was a surprise to find these on Mars and what that means, I guess, to you as a geologist as far as looking for a suitable sample to bring back to Earth? And you mentioned a little bit about the microfossils and similar rocks on Earth. Thanks.
Yeah, I think silica was one of those materials that we were very hopeful for. And when it popped up, it was exciting, no question about that. I think, as Patrick was saying, when you see this material in its geological context, you get a lot of information out of it. So I would say, first of all, that the silica was not just crystalline. A big fraction of the rock is made out of amorphous silica. Some materials we're familiar with, like opal CT and maybe a thing called opal A as well, are very important because this type of silica on Earth will form in environments where it can precipitate very quickly, and if there is a microorganism there, it can entomb them before water, which is the essential substance of life, interacts enough that the organic matter breaks down. So almost all occurrences from the early Earth, and I'm talking rocks that are billions of years old, almost every example that we have are things that are preserved in what were regarded to have formed early on as amorphous silica. So I think this is a tremendously exciting discovery. Kind of building a little bit on what Emily was talking about, as we drove the rover along, we would have loved to have found more silica in the Murray Formation again, and we just simply haven't. So there are some models that predict enrichment of silica that I think, through the absence of the silica in the rocks that we see, we recognize now that the part of the Murray Formation that contained the silica was really very special. And I think it points to a context where the accumulation of the silica really is part of the primary environment and the kind of rocks that were being eroded to supply material into the lake at that time.
Paul Doherty, the Exploratorium. Can we have a rover health update?
Yes. First, I'll tell you about a few of the things, and then I'm going to let Ashwin tell you about the drill. Everything's in good shape with these exceptions. So with the REMS, the meteorology experiment, all the sensors are working, except we're having some difficulties with the wind sensor. So what still works fine is the temperatures, humidity, pressure, and UV radiation, and we're diagnosing the issue with the winds, and we will soon be taking some pictures with the close-up camera on the end of the arm of the wind sensors to take a look to see if there's anything we can see wrong that way. DAN instrument was measuring hydrogen in the ground. It has an active mode and a passive mode. We were having some issues with the active mode, but the problems have gone away, and so it's back to complete normal operations. We can do either passive or active. A lot of times the reporters ask about the status of the wheels, which have all these holes in it, which were punctures from driving over sharp rocks, and those are doing pretty well. And we haven't broken a grouser yet. That's the chevron pattern that runs across the wheels. Once a single wheel has got 3 broken grousers, we know from extensive testing on Earth that we will still have 60% of the life of that wheel left. So we can definitely get to well into the sulfate unit in our mission and have no problems with that. So the main other aspect that we're having issues with right now is the drill, and Ashwin Vasavada is going to take that question because he's up on the latest status.
Okay, thanks. Yeah, I'm the current project scientist for the Curiosity rover mission, Ashwin Vasavada. And yeah, it's sort of late breaking news, so I agreed to field this question if it came up. You may recall that we've told you about 3 different types of issues that we've been investigating with the drill. The drill has a percussion mechanism, the main mechanism that chisels into the rock. It's designed to have a chiseling drill bit that rotates as well. That percussion mechanism has been showing an electrical short since quite early in the mission, Sol 911, and it has been intermittent, and we've been able to use the drill in spite of that intermittent electrical short. The second thing we told you about maybe a year ago or so was a motor within, on the end of the arm, within the sample processing system that's located on the end of the arm that kind of sifts and moves around sample once you've drilled it. There's a little motor that opens a door and exposes a chamber, and that motor had stalled, and we were able to diagnose that stall, and then it was intermittent, but now it's largely, the problem's gone away, so that's a good one for us. We no longer are too worried about that particular one. This third one, which we just told you about last week in a press release, was with a mechanism called the drill feed. And so you can imagine we put the arm down on the surface. It has these 2 prongs that you've seen in pictures. You press against the surface to keep the drill in place. And then a mechanism moves the actual drill up and down to do the drilling. That's called the drill feed. And that mechanism exhibited a stall last week, actually weekend before last. And since then, we've been running activities on the rover to diagnose that issue. We had narrowed it down, as we told you last week, to either a problem with a brake that's very much internal to the motor itself, or what's called an encoder, these electrical sensors that tell us how the motor is rotating. We were able to determine that it was the brake that's most likely the issue at this point, we think. And we were able to get some partial success in actually moving the drill feed and uninstalling it, if you will. Since then, what's just happened in the last few days, we've now determined that that problem is recurring. It went away, and we were very excited, but then it unfortunately has returned again in just the last day or so. So we're in the process of still figuring out how to go recover the operation of that drill feed. So, long answer, but that's where we are with the drill.
Okay, are there any more questions from reporters in the room? Any more questions on the chat?
Yes, Emily has another one. What does it mean geologically that the sulfate veins are getting so much more pervasive?
John, if you want to talk that.
I don't know, Emily. You know, the rock's getting more fractured, and you know, it could be, one can imagine an interesting limit to that that we never thought of before, where the so-called sulfate unit from orbit just turns out to be even denser accumulations of fractures. It'll be fascinating to see if this is something that relates to the primary layering or whether it relates to the overprinting history of fracturing.
For the fracturing itself, is it thought to be because of differential composition and temperature change, or water included in the rock?
Oh, there's no question that it has to involve a process that is followed by water. So there's the team, a couple people on the team have published some papers, and there's general consensus that the fractures form because of the deep level of burial. We infer that for a couple of reasons, but most recently, yesterday, Kevin Lewis gave a talk on rover gravity data, which suggests the overburden may have been as much as a couple of kilometers. So even 100 meters, a couple hundred meters of burial is enough to have rock extend and fracture, and then as long as the water is there in the groundwater system, it'll fill up, percolate, and precipitate that salt.
Okay, any more questions from reporters in the room? Questions on the chat?
Alice Chang from the Associated Press is asking a follow-up on the drill. What is Curiosity currently doing as engineers are diagnosing the drill issue? How long before it moves again?
So, you know, as a scientist on the team, I can best describe it maybe as you walk into the room and it's one of those sort of Apollo 13 moments where all the engineers are huddled around and thinking to be as clever as they can be of what they can do to run certain activities on Mars that would give them insight into what's going on with the drill. The real challenge is, of course, you can't go up there and take it apart, which is really the way you'd figure out what's wrong with it. So they basically are running a series of tests that, as carefully as they can, kind of separate out various hypotheses they have of what could be going wrong. So, you know, you can imagine this actually exists, a big diagram on the wall sort of all the different ideas that could be causing this particular problem that we see in the data, and then tests that can isolate each potential cause. And so that's how they determine that it most likely is something deep inside the motor as opposed to something, you know, outside that's causing the feed not to work, like a rock or something. It's something inside the motor that led to the idea of the brake. They were, I guess, this new information that it is now intermittent, now throws their analysis in a different direction. So they're again coming up with a new set of tests. And that's part of the reason we haven't been able to use the rover a whole lot for other activities such as driving or, of course, continuing to drill. So we're a little bit, you know, as a science team, we've been waiting for a couple weeks to be able to do things like use the arm or drive again, but we're keeping busy with using the other instruments on the rover while they do these tests.
Any more questions on the chat?
We have a question from Eric Berger with Ars Technica. Can you generally describe what the lake would have been like during the period when it was most favorable for life? And was this about 3.8 billion years ago?
So throughout its whole history, just to summarize quickly, so we believe that the 200 meters of rock was not always representative of a lake. There were some times when it was dry, and the groundwater would have been important, but when it comes back, there were times when it was relatively pH neutral. There were times when it was more acidic. The groundwater may have been more neutral, more acidic, but never, based on the data that we have, did it ever exceed the window for easy, what I would call easy habitability. We're not even sure we need to appeal to chemolithotrophic organisms that have to be really extreme. So for that entire history, it seems to have been favorable.
Okay. Any more questions from reporters in the room? Any more questions on the chat? Okay, this concludes our press conference. So we'll take a break for lunch and we'll reconvene at 1:30 with tracking the orientation of the terrestrial planets.